My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Design and Analysis of Algorithms as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define algorithm specification. Algorithm specification. An algorithm specification is a clear and step-by-step description of how a problem should be solved using an algorithm. It explains what the algorithm will do, what inputs it will take, what outputs it will give, and how it will process the data. This makes it easy for programmers to write correct and efficient code. A good specification should include: 1. Input, what data is needed. 2. Output, what result will be produced. 3. Steps, the method or process to solve the problem. 4. Constraints, any rules or limits, like time or memory. Example: to find the largest number in a list. Input, a list of numbers. Output, the largest number. Steps: 1. Start with the first number as the largest. 2. Compare each number with the largest. 3. Update if a bigger number is found. 4. Print the largest number. This way, algorithm specification acts like a recipe for solving problems, making it easy to implement in programming. Next important short question is: 2. Trees. Trees. A tree is a way of organizing data in a hierarchical structure, like a family tree. It is made up of nodes, points, connected by edges, lines. The top node is called the root, and nodes connected below are called children. Nodes that have no children are called leaves. In a tree, there are no loops or cycles. It looks like an upside-down tree in nature. Trees are used to store data in a way that is easy to search, insert, and manage. Key terms: root, the top node. Parent and child, connections between nodes. Leaf, node with no children. Height. Longest path from root to a leaf. Example: think of your family tree. Your grandfather is the root. Your parents are children of the root. You are a leaf node. Trees are used in file systems, databases, searching, binary search tree, and AI because they organize data neatly. Next important short question is: 3. Dictionaries. A dictionary in data structures is like a real-life dictionary where you search for a word, key, to find its meaning, value. In programming, a dictionary stores data in key-value pairs. Each key is unique, and you use the key to quickly access its value, making searching and updating data very fast. Key features: key, a unique name or number. Value, the information linked to that key. Fast access, you don't need to search the entire data, just use the key. Example: imagine a phone contact list. Key, friend's name, Rahul. Value, phone number 9876543210. Searching Rahul directly gives you his number. Dictionaries are widely used in databases, caching, and language translation apps because they save time by providing quick lookups. Think of it as a fast and smart cupboard where every drawer, key, is labeled, so you instantly find what's inside, value. Next important short question is: 4. What is a priority queue? A priority queue is a special type of queue where each element has a priority. Instead of being served in the usual first in, first out, FIFO, order like a normal queue, elements with higher priority are served first. If two elements have the same priority, they follow the order they were added. Key points. Each element has a priority value. High priority elements are removed first. Can be implemented using heaps, arrays, or linked lists. Example. Think of a hospital emergency room. A patient with a serious injury, high priority, is treated first. A patient with mild fever, low priority, waits even if they arrived earlier. Priority queues are used in CPU scheduling, Dijkstra's algorithm, shortest path, and printer job management, where some tasks need attention before others. Remember, a normal queue is like a line at a ticket counter, but a priority queue is like VIP service, important people, or tasks, go first. Next important short question is 5. Write any two applications of stacks and queues. Applications of stacks and queues. Both stacks and queues are important data structures used in daily life and computer science. Applications of stack, LIFO, last in, first out. 1. Undo redo in editors. When you type in MS Word or Google Docs, pressing undo takes back the last change. This works because the last action is stored on top of a stack and removed first. 2. Expression evaluation. Stacks are used to calculate mathematical expressions, especially in compilers, making programming languages work. Applications of queue, FIFO, first in, first out. 1. Printer queue. When many people send files to a printer, they are printed in the order they came in, just like a queue at a shop. 2. Customer service systems. Call centers use queues so the first caller gets help first, keeping things fair. Easy trick. Stack is equal to pile of plates, top plate goes first. Queue is equal to bus queue, first person enters first. Next unit 1. Long questions. First important long question is 1. Explain performance analysis of algorithms in detail. Performance analysis of algorithms. Performance analysis of algorithms means studying how good or bad an algorithm is in terms of time, memory, and other resources. In simple words, it helps us understand if our solution is fast and efficient. This is important because in real life, data can be huge, and we want programs to run quickly without using too much memory. Types of performance analysis. 1. Space complexity, memory used. It measures how much memory an algorithm needs to run. Includes memory for inputs, variables, and function calls. Example, a simple algorithm to reverse a string might use extra memory to store the reversed string. 2. Time complexity, execution time. It measures how fast an algorithm runs as input size increases. Focuses on counting steps, not exact time in seconds. Example, searching for a name in a phone book. Linear search. Check names one by one O(n). Binary search, keep dividing list in half O, log n, much faster. Types of time complexity cases. Best case, the algorithm works in the least time, lucky case. Worst case, the algorithm takes the most time, guaranteed upper limit. Average case, time for typical inputs. Why performance analysis is important. Helps choose the best algorithm for large inputs. Saves time and memory in real-world applications, banking apps, shopping sites, etc. Makes software faster and cost-effective. Easy example. Imagine searching your friend's name in your contact list. If you check one by one, it's slow, O(n). If the list is sorted and you divide it into halves, it's faster, O log n. That's the power of analyzing performance. Tip to remember. Think of performance analysis as planning your journey, choosing the shortest and fastest path to reach your goal. Next important long question is: 2. Describe different elementary data structures with examples. Elementary data structures. Elementary data structures are the basic ways of organizing and storing data in a computer so that we can use it easily and efficiently. They are the building blocks for designing algorithms and solving problems. Let's understand them one by one. 1. Arrays. A collection of elements of the same type stored at continuous memory locations. Accessing elements is fast because we use an index. Example: a list of student roll numbers, R0 is equal to 101, R1 is equal to 102. 2. Linked list. A chain of nodes, where each node has data and a pointer to the next node. Useful when data size changes often. Example: a train where each coach, node, is linked to the next. 3. Stack, LIFO, last in, first out. Items are added and removed from one end, top, only. Example: a pile of plates, the last plate placed is removed first. 4. Queue, FIFO, first in, first out. Items are added at the rear and removed from the front. Example: a queue at a ticket counter, the first person gets the ticket first. 5. Tree. Data is arranged in a hierarchical structure with a root node and child nodes. Example: a family tree with grandparents at the top and grandchildren at the bottom. 6. Graph. A collection of nodes, vertices, connected by edges. Example: a map of cities connected by roads. Why important? These structures make searching, sorting, and updating data faster. They are used in databases, operating systems, social networks, and AI. Easy trick. Arrays is equal to fixed storage. Linked list is equal to flexible storage. Stack is equal to backtracking. Queue is equal to scheduling. Tree is equal to hierarchy. Graph is equal to networks. Next important long question is: 3. Discuss the working and applications of sets and disjoint set union. Sets and disjoint set union. A set is a data structure that stores a collection of unique elements. It does not allow duplicates and is useful when you only care about whether an element is present, not how many times it appears. Example: set of fruits is equal to apple, banana, mango. You can quickly check if banana is in the set. Working of a set. A set supports operations like: 1. Insert, kiss smiley, add element X. 2. Delete, kiss smiley, remove element X. 3. Find, kiss smiley, check if X is present. Sets are often implemented using hash tables or balanced trees for fast operations. Disjoint set union, DSU, union find. A disjoint set union is a data structure that keeps track of a collection of non-overlapping sets. Each element belongs to exactly one set, and sets are combined when needed. It supports two main operations. 1. Find, kiss smiley, tells which set an element X belongs to, find the parent. 2. Union, X, Y merges the sets that contain X and Y. Example: imagine 5 students in 3 separate groups. Group 1 A, B. Group 2 C. Group 3 D, E. If we do union B, C, groups 1 and 2 merge, A, B, C. Applications of DSU. Network connectivity, to check if two computers are connected in a network. Social networks, find if two people are in the same friend group. Graph algorithms, used in Kruskal's algorithm to find minimum spanning trees. Image processing, to detect connected components in images. Easy tip to remember. Think of DSU as managing friend circles. Find tells you which friend circle a person belongs to. Union merges two friend circles into one. Next important long question is 4. Explain graph representations and operations in detail. Graph representations and operations. A graph is a data structure made of nodes, vertices, connected by edges, links. It is used to represent relationships like cities connected by roads, social media friends, or computer networks. There are two types of graphs. Directed graph, edges have a direction, like one-way roads. Undirected graph, edges have no direction, like two-way roads. Graph representations. 1. Adjacency matrix. A to D array where matrix I, J is equal to 1 if there is an edge between vertex I and J, otherwise 0. Good for dense graphs, many connections. Example. For vertices A, B, C. ABC. A010. B101. C010. Each vertex stores a list of its neighbors. Good for sparse graphs, few connections. Example. AB. BAC. CB. Basic graph operations. 1. Add vertex, insert a new node into the graph. 2. Add edge, connect to nodes with a link. 3. Remove vertex edge. Delete a node or connection. 4. Search traverse, visit all vertices using BFS, breadth first search level by level. DFS, depth first search, go deep along one path first. 5. Find degree, number of edges connected to a vertex. Applications of graphs. Google Maps, cities and roads. Social media, friends and followers. Networking, computers and connections. AI and games, pathfinding and decision making. Easy tip to remember. Adjacency matrix is equal to table, quick lookup, uses more memory. Adjacency list is equal to notebook, saves memory, great for large graphs. Next important long question is 5. Analyze the advantages and limitations of randomized algorithms. Randomized algorithms, advantages and limitations. A randomized algorithm is an algorithm that makes random choices during execution to solve a problem. Instead of always following a fixed path, it uses randomness to improve speed or simplicity. These algorithms are especially useful for large and complex problems where a fixed method would take too long. Example. Imagine finding a specific card in a shuffled deck. A normal algorithm searches one by one. A randomized algorithm may randomly pick cards, which sometimes finds the answer faster. Advantages of randomized algorithms. 1. Simplicity. They are often easier to write and understand because randomness simplifies logic. 2. Speed. Many randomized algorithms are faster on average than deterministic ones. Example, quicksort with random pivot selection. 3. Efficiency for large inputs. Useful in problems with huge datasets where deterministic solutions are slow. 4. Versatility. Can handle complex tasks like hashing, machine learning, and cryptography easily. Limitations of randomized algorithms. 1. Uncertainty in output. They may not always give the same result every time. Some algorithms might fail occasionally. 2. Not always optimal. The result may not always be the absolute best, especially in optimization problems. 3. Difficult to debug. Since they use randomness, finding and fixing errors can be tricky. 4. Extra randomness requirement. They depend on generating random numbers, which needs good random number generators. Quick recap trick. Randomized algorithms are like guessing games with a plan. They use luck to save time. Good, simple, fast, and great for large data. Bad, not always predictable or perfect.